Recall for our stiffness term, we have our weight basis function differentiated with respect to x. So in this case, we're using a Lagrange basis. We need to determine what the derivative of our Lagrange basis is. Ideally, we'd like to avoid having to numerically differentiate it. So if we could arrive at some sort of analytical expression, that would be superior. And we are able to do that using a technique called logarithmic differentiation. The basic idea is that for any general function, the derivative of the function over itself is equal to the log of that function. So this is commonly useful for when you'd like to reduce some sort of function from a product of many terms into the sum of many terms. So therefore, we don't necessarily care so much about its ability to do that. However, we can solve this for f prime. So in other words, if we multiply by our function on the other side, we can get an explicit representation of the derivative of a function. And then it just so happens that the effect of the log on the product in the Lagrange basis allows us to construct a closed form expression. So we can see here then the derivative of our Lagrange is our Lagrange basis times the log of our original basis. So we went from a product of some terms to the sum of some subset of those terms. So we can use our previous function that we developed for our Lagrange basis, and we can get a piece of code snippet here that allows us to calculate our derivative of our Lagrange basis at any point. And this is again vectorized, so we can submit a vector of points that we'd like to calculate our derivative at, as well as we can submit a vector of any and all bases in that Lagrange space that we'd like to evaluate for. If we want to specifically evaluate at the interpolation points, we need to do a little bit more of an involved method to avoid singularities and things of that nature. Alternatively, if you'd like, you could use the Lagrange function, but rather than trying to evaluate explicitly at your quadrature points, you can evaluate arbitrarily close to your quadrature points. So in other words, we'll subtract the smallest floating point difference we can from our point, so that will essentially avoid our singularity, and the error here is comparatively pretty small.